All right, from Atlanta.
Oh, Minu is here. Professor Hedeker. Minu is our director for this responsible innovation and entrepreneurship.
Oh, very nice to meet you.
Why we are
Hi,
still.
John. I'm sorry, I'm in a hotel, so my connection's not good.
Oh, that's okay. Well, I hope you get something out of it, even if it's only a fraction of it.
Well, I attended the class, so I kind of know some of the content. So I took your class. So
okay, good. Well, this will be boring then for you.
Looking forward to this one, though.
I think I will give it like about like 1 or 2 minutes, and then we'll start. Yeah.
Sounds good.
Feel free to introduce yourself on the chat. Thank you so much. Majority of the attendees will be from San Francisco State University and also CSU system, our California State University system.
Oh, good. Yeah.
And also our, fellow researchers from Germany, Kiel University. We also have some collaborations. Yeah.
All right. Got somebody from West Virginia University.
Oh, yeah.
So all over the place.
Atlanta. Oh, that's awesome. Welcome, Ling. Oh, marketing PhD. We also have PhD students here. That's awesome. Okay, now I think let's get started. Thank you so much all for joining us today. I'm really thrilled to welcome you to our second virtual research brown bag of the semester. As always, we are cooking up some exciting insights as part of the Responsible Innovation and Entrepreneurship Initiative at San Francisco State University Lam Family College of Business. And I am Chen Wei, Associate Professor of Management from SFSU. So for those of you who are new here, I will give you a brief review of our research initiative. The main goal of this Research Brown Bag series is to share some cutting-edge scholarship in the field of responsible innovation and entrepreneurship, as well as learn some fancy research methods. And we have 2 talks every semester, 1 research domain talk and 1 research method talk with guest speakers from, different fields and who are experts. And we try to make it like fancy, potluck, where everyone bring their own intellectual dish to share. So feel free to kind of be as chatty and engaged as you like. As the moderator, I will be keeping an eye on the chat and where you can post any questions and comments you have throughout the presentation. I will be also keeping us on track and making sure we stay on schedule, as we've got like 90 minutes of awesomeness ahead of us. It is my great pleasure to introduce today's guest speaker, Dr. Donald Hedeker. He is a professor of biostatistics from the University of Chicago, and he specialized in statistical methods for clustered and longitudinal data, and have authored the book Longitudinal Data Analysis with Robert Gibbons. I remember I read this book during my PhD program. And Dr. Hedeker's recent research focused on developing methods for analyzing intensive longitudinal data collected through mobile devices and the internet, which is increasingly used in areas such as mobile health and ecological momentary assessment studies. He's a fellow of the American Statistical Association and also an elected member of the International Statistical Institute. Dr. Hedeker has also received several prestigious awards, including the Sales Award for Distinguished Multivariate Research from the Society of Multivariate Experimental Psychology in 2022. And also since 2006, he has been an associate editor for statistics in medicine. So we are really thrilled to have him share his insights with us today. Without any delay, I will hand it over to Dr. Hedeker to take us on an exciting method journey. Thank you.
Okay, thanks very much, Chen-Wei, for the nice introduction. And let me share my screen. And thanks also to Manu for inviting me to be here this afternoon. Okay. And so, as mentioned, what we're going to talk about today is introduction to multi-level modeling. And it's an area that I've been involved in for quite some time. So you might say, to begin, what are multi-level data? So multi-level data are hierarchically structured, nested, clustered, where you have data collected from units organized or observed within units at a higher level. For example, you might have data collected on students and they're observed within classrooms, and you have data both about the classroom and the student. Or you might have familial data where you have data collected on siblings, but you also have family data. And then in the longitudinal context, you have repeated observations clustered within subjects or individuals. And all of these are examples of what are called two-level data. At level one, we would have, for example, students, and that's where your primary dependent outcome variable would be, and then some other mediating variables or other kinds of covariates. But additionally, you have information about the cluster, for example, the classroom, and there might be variables there that influence the student's outcome. And that's what we're going to get to today, is to see examples of how the clustering, be it a classroom, a family, or an individual, can influence the data collected within those clusters. So what is multi-level data analysis? Here's an old definition, but it kind of rings true. Any set of analytical procedures that involve data gathered from individuals and from the social structure in which they are embedded. Okay, so that's all about multi-level data, and are analyzed in a manner that models the multi-level structure. So that's the important part about the analysis. It's going to model that structure. Okay? And so it recognizes the influence of the structure on the individual outcome. So in your field, you might have information on employees within firms or individuals within companies or something like that. It's the same kind of idea. Okay? So we have data on the structure, and we have data on the individuals within the structure, and we want to put this all together in a statistical model. And again, in the longitudinal context, what we have is the structure is the person, individual, and we have repeated observations measured on the person. We want to take this into account. So why do you want to do multi-level data analysis? Well, one thing we can learn about it is we can learn about, well, how much variability is there at each of these different levels? So, you know, how much variability is there, let's say, at the family level and at the individual level? And it allows us to model the level one outcome in terms of effects at both of these levels and even interactions. So it gives a real flexible framework for modeling multi-level data. Now, from a statistical point of view, the reason we go to these models is that the responses are not what are said to be independent. There's a correlation in the data that needs to be taken into account to give us proper statistical inference. Okay? And so ultimately, I think of multi-level analysis, it's an example of what I think of as a golden rule of statistic. One person's error term is another person's career. All right, so some people might ignore it, but hey, I'm saying, no, it's important. Bring it into the model. So it's got to be put on this chart here that shows all these different golden rules and different religions. We got to put in multi-level modeling here as well. All right, so let me show you a little bit about the data structure before we get to some examples. Here is what the data structure might look like in the clustered context. Okay, so here, first variable I might have on the left-hand side is a cluster identifier. Here it's just going sequentially from 1 to large N. Okay, so say there's 100 clusters, something like this. Then within each cluster, I have a row for the different subjects in that particular cluster. Now, the important thing there is to realize the number of rows, N sub 1, N sub 2, et cetera, can be different. So there's no assumption that the number of subjects within a cluster that's equal, okay? Because in most data sets, that's not going to be equal, right? It's going to be quite varied. And so this modeling technique allows for that possibilities. Now, we might also then have variables that are measured at the cluster. For example, it might be a cluster randomized trial in which some subjects get a control, some subjects get an intervention. But in that case, every person, let's say in this first cluster, has the same group, okay? Likewise, we might have the size of the cluster as an important variable. Same idea. This is at the cluster level. So in a way, there's some redundancy you can think about in this data set in the sense that everybody within the same cluster has the same values on the cluster variables. But of course, it changes from cluster to cluster, those things. Okay? And then we have data that does change within clusters, that is at the subject level. So like the dependent or outcome variable. Okay? And we might record their sex, their age, things like that, demographic variables. Okay? So this is the way the data are structured to get to the multi-level data analysis. And so here, when I get to a few equations, and I won't bore you with a lot of equations, but some, I'll use I to designate the clusters and J to designate the subjects within the cluster. And again, number of subjects per cluster can be different. Now, interestingly, longitudinal can be set up the same way. But again, here, the cluster, as it were, is the subject. Okay, so here, let's say I got a study with 100 subjects or so. Okay? And within each row is the measurement of a subject at a particular time point. Okay? So again, here, an important aspect is that the number of rows for each of these subjects can be different. So there's no assumption that subjects are measured at all the same time points. Okay? So there can be some missing data, as it were, within the study. Okay, and that's an important aspect for sure in longitudinal, that the number of time points per subject is allowed to be varied. Okay. And again, we might here have some variables that don't change across time, said to be time invariant variables. So it might be a study where people receive different treatments, okay, but across time they're in the same treatment group. Okay. Or again, we might record demographics like sex or age, which don't change. Now, admittedly, age does change across time, but we might have something like baseline age, right? And so that would be a constant across these measurements. And then we're going to have variables that do change values across time. So the dependent variable, I mean, that's why we do a longitudinal study. We want to learn about how does the dependent variable change across time? And does it change differentially for different subjects? That's what we're going to get to. And we might have some other variables, like let's say if it's a drug trial, we might have the dose of the drug that they're on, and that might change across time. But realize the skeleton of the data is the same as in the clustered case, right? In these two cases. Okay. Now, these models, you might have heard them referred to as multi-level models. You might have heard them referred to as random effect, random coefficient models, mixed effect models, hierarchical linear models. In different literatures, they sometimes use somewhat different terminology, but they're really all the same kinds of models. Okay. And as I'm going to show, hopefully this morning or this afternoon, depending where you are, or even this evening, if you're in Europe, that these methods are useful for analyzing clustered data and then also longitudinal. So we'll start with a clustered example, and then we'll also get to longitudinal. Now realize you could have both, right? You could have repeated observations within subjects and then subjects within, say, hospitals or firms or clinics or something like that. Well, that would lead to what's called a three-level kind of design and analysis. And the methodology extends to these higher levels as well. So that's possible. This afternoon, I'll focus only on these two-level situations. All right, so I know you've been saying enough with the talk. Let's see the equations. Everybody always wants to see the equations, right? Show me the Greek letters. I want to see those, right? All right, so here, the main point I want to make with this equation is to show you that this is really just one simple step up from multiple regression. Okay, so if I don't include that term here where my little hand is over, I just have y equals x beta plus error. Okay, so that's multiple regression, right? We have a dependent variable, we've got x, and we've got some regressors, covariates, explanatory variables, independent variables, whatever you want to call the x variables. And we've got error term, right? That's multiple regression. So what all the things you learn about in multiple regression apply here in multi-level. Namely, x can be continuous variables like age, could be dichotomous variables like sex, it could be polynomials like linear, quadratic, could be interactions, all of those things. So everything in multiple regression applies here because this is multiple regression, but we're adding in one additional term, and that's the cluster effect. Because we want to learn about how does the cluster a person is in, how does that influence their outcome? Now, in the way I'm writing this, the cluster effects are said to be, quote, random effects. What does that mean? It means that we're conceptualizing the clusters we have in our data set as being a representative sample of some population of clusters that we want to make inference about. Okay? So let's say we're doing an educational study. We have 20 schools from the San Francisco area. What we're thinking is that these schools represent some sampling of the population of schools that we want to speak of. Okay? So that's why they're random effects. And when a variable is a random variable in statistics, it means it has a distribution. And so what we're assuming here about the random cluster effects is that they have mean zero, they're deviations relative to the x beta part of things, and they have a cluster variance. Okay? And really, it's that cluster variance parameter that is what makes this special relative to ordinary multiple regression, because that's going to tell us essentially how much influence do the clusters have on the subject outcomes. Because think about this, if the clusters have no effect, all of these epsilon i's, I know it looks like v's or u's, it's the Greek letter epsilon, all of them will be like zero. And then the cluster variance will be very small. And that will be a situation where the clusters have very little effect on the student outcomes. On the other hand, let's say the clusters have quite a bit to do with the student outcomes. Then these cluster effects will be different from zero, and the cluster variance will grow. Okay? So as we'll see, the cluster variance is an important thing to recognize how much effect is there of the clustering on the data. Okay. So notice this also, as the cluster subscript is present for all of these things, again, we're making no assumption that the cluster sample size is the same. It can be different. And the covariate matrix X can include, again, variables at cluster level, subject level, interactions. Okay? Okay, so just multiple regression, really, but with this added twist. Okay? And this is the added twist, adding in the random effects. Okay? So this is what distinguishes the model from an ordinary, or what's sometimes called a fixed effects multiple regression model. Okay? And it represents the effect of subject clustering. And there's going to be one of these for every cluster. In fact, I'm going to show you how you can look at these to learn more about what's going on with the data. Okay? And as I mentioned, if subject clustering doesn't have much effect, these are going to be close to zero, and the cluster variance will be very small. Okay? On the other hand, if subject clustering has a strong effect, okay, then these will deviate from zero, and then the cluster variance is going to be considerably larger. Okay? So the cluster variance, again, is a key parameter here that informs us about how much multi-level, how much the multi-level structure is important. Okay? Okay, now this just shows the statistical. If you go look at a statistician, they'll write it like this. Okay, so it's just one line, really. One can write it this way. If you look at this, you'll see the mean x beta. That's the same as in multiple regression modeling, but the latter part, the variance, is what takes into account the clustering. And what this ultimately leads to is oftentimes the cluster variance is expressed as what's called an intra-class correlation. Okay. What's done here is we have in the numerator the cluster variance, and in the denominator the sum of the residual and cluster variance. And this tells us the proportion of the variability that's accounted for by the clustering. Okay. And so this is going to be a statistic we're going to generate, the ICC, or intra-class correlation. Now, some people have argued that class is not a great term for this, because in educational studies, for example, class means classroom. And so it might be a little confusing. So Harvey Goldstein, for example, who's a leader in this area, has proposed instead, you replace it with, say, intraclinic correlation or intraschool or intrafamily, interfirm, et cetera. And admittedly, that's maybe a little bit more precise way of stating this idea. Okay. Now realize this intraclass correlation, where does it live, first of all? Well, the lowest it could be would be 0. If the cluster variance is 0, it's 0, right? On the other hand, the largest it could possibly be would be 1. That would be if the residual variance would equal 0. So it's really like an R-squared kind of measure. And it tells us really what I have here is this bullet, the proportion of variability of the dependent variable, which is attributed to the clusters. So how much of the variability, for example, in students' grades are attributable to the classroom? And how much is attributable to the student? Now, in parentheses, you say unexplained. What's that all about? Well, because if we go back to the equation here, it's what's unexplained by X beta, by the regressors in the model. Okay. All right. So the ICC can change depending on, what we're trying to explain the outcome with. So the more, the X part of things explains why, the little additional variance there will be. Okay. So that's important to realize it can change depending on how many regressors we have in the model, possibly. Okay. Now, if you look at different kinds of clusters, people have looked at this for a while. It tends to be larger for clusters that are smaller, and it tends to be smaller for more diffuse clusters. Okay. So, for example, if you have data on spouses, they tend to be a little bit more correlated, right, than if you have data on patients from physicians or individuals within counties. I mean, it makes sense. If you think about it, you're probably closer to your spouse or your partner in terms of attitudes, let's say, than the people on the block that you live on or something like that. Okay. So that's all that's about. But now, interestingly, it could change depending on the dependent variable too. And here I have an example early on in my work in this area that I did with Regina Casper, who was a psychiatrist working on a study with anorexic women that I found really interesting example. Now, this is a small study. It had data on 63 sisters from 26 families. And here, the first variable I looked at was their height. Okay, so height, we know this is correlated within families, right? So here it's in inches, so you can see the intercept 6'4", that's 64 inches, 5'4". Okay. And then here I have the family variance and then the residual variance. So I take the ratio of the family variance to the sum of these two, I get an ICC of 1/2 about. So obviously, within families, height is very correlated. Okay. Not perfectly so, but pretty highly correlated of about 0.5. Now, here I also looked at a psychological factor, and me being the stupid statistician, I didn't write down which one it was. So I don't know, maybe it's anxiety, depression. I'm not sure which one it is. But in any case, when I do this, get these estimates, I get an ICC of about 1/3. So it's probably something like temperament or something like that. So the sisters are similar to each other for sure, but not as strongly so as biological measure like height. Okay. Now, interestingly, I then looked at the BMI, body mass index, for these sisters. And this is the example I thought that was quite telling, because if this was kind of in a normative kind of sample, BMI would be pretty highly correlated within family members and probably pretty close to like what height you see for height. But here, notice the family variance goes to 0. Why? Because one member within the family was suffering from anorexia and had an abnormally low weight, right? So made this correlation within families essentially go to 0, okay? So this is an interesting example in the sense that BMI would ordinarily be highly correlated within sisters of a family. But in this particular population, where one of the individuals was suffering from anorexia, had this very low weight, we see this kind of result. Okay, so the point is to realize is that there are general rules about ICCs, but it kind of depends on the variable you're looking at, as you can see here, but it also depends on the population that you have your measurements made on. Okay. All right, so let's get to an example. Now, this is a kind of an old example. When I was looking at the slides earlier, I thought, my God, that's almost 30 years ago. I've been doing this for far too long. But this is I thought, a very useful data set to show kind of the advantage of multi-level modeling relative to not taking the multi-level structure into account. So I want to present it here. And we published it in a psychological journal, Journal of Consulting and Clinical Psychology. It was a study. Yes, question.
Professor Hedeker, before
Sure.
you dive a little bit deeper into it, we have a few questions on the chat.
Sure.
Yeah, and the first question here is about data structure. Like, is there any formal rules about the minimum number of subjects in each cluster?
Not necessarily, but just realize if I mean, this can also accommodate clusters that only have one subject within it. It's just that those clusters wouldn't provide you with too much information. So if there's less data, there's less information, but there's no rules about the minimum numbers per se. Now, having said that, the number of clusters you have, there's some guidance about that. Because we're treating this, let me go to the equation, as a random effect, and therefore we're estimating the variance there. If we say only had 5 clusters, we would not have much information to estimate this variance. Then what generally people would recommend is, instead of treating it as a random effect, put 4 dummy codes, treat it as a fixed effect to account for the differences, because you don't have much information about estimating this population parameter. On the other hand, when you get to about 15 clusters or so, then that's generally deemed reasonable. When you're sort of in between 10 and 15, you're kind of in this gray area. Of course, what you can always do is sensitivity analysis, do it using dummy codes as a fixed effect, do it as a random effect to see to what extent your conclusions are the same or not, see how much they vary. That's always a good idea.
The second question here is, how does this analysis differ from ANOVA? And so the ICC values differ with the number of clusters. Every cluster will have different ICC values.
No, there's only one ICC. Realize here, the formula for the ICC, it's just saying the cluster variance, which is just one value here, divided by the cluster variance plus the error variance. So there's only one ICC. Okay. Now, you could, if you extended this modeling, you could see if the ICC varies between, say, these kinds of clusters and these. One could further extend this model, but what I have so far, I'm assuming one ICC.
Is there a range we might need to consider?
Well, generally, again, the range of the ICC depends to some extent on, how diffuse or how compact is the cluster. Depends on the dependent variable. It depends also on the outcome. Now, what I'm going to show you with this example, which I found kind of interesting, is that the ICCs I get in this educational example that I'm going to present, they're not that big, but they do make a difference in terms of the statistical inference, in terms of the p-values, in terms of your conclusions. So I would say even small ICCs can be rather important. Any other questions?
Thank you so much. We have one last one here.
Okay.
Can I say I'm using multi-level analysis if I'm using clustered standard error?
Yeah, if you're doing clustered standard errors, I wouldn't especially call that multi-level analysis per se. What you're doing in that context is you're doing something like ordinary regression, but realizing your standard errors aren't quite right and trying to fix those. But what I'm going to show you in doing multi-level is this. We're going to get estimates of these random effects that you would not get if you do what's being asked about, which is just doing adjustment to the standard errors. Okay, so it's in a similar vein, but it's not quite the same thing. All right. Well, feel free to ask further questions, and Chen Wei, if you want to interrupt me at any time, please feel free to do so. I just get very excited about this topic, so I tend to go on and on. All right, so this is a study that was actually done in California by a former collaborator of mine, Brian Flay, was done in Los Angeles, so in Southern California. And it's an educational study that looked at the effects of television and family smoking prevention on students in 7th grade. And these 7th graders were clustered within classrooms and then also within schools in Los Angeles. Okay, so this is we're going to see is a 3-level structure. We have students within classrooms within schools. And what I'm going to first do is to do 2-level analysis, students within classrooms, let's say, and then we'll extend it to the 3-level. And you can see the numbers of students per classroom and classrooms per school is pretty varied. Now, the outcome I'm going to look at is the knowledge of their knowledge about the effects of tobacco use. Okay, so tobacco use, as we all know, is a really not a good thing, right? And so we're here. The study was aimed, and why it's called prevention is if these kids hadn't yet tried smoking, to get them prevent from trying, and if they already had started, to get them to quit. That's what the cessation part is. And students were tested both before and after an intervention here. That's the timing. And this was a cluster randomized study in which schools were randomized to 4 different treatment arms. One arm got what's called a social resistant classroom curriculum, in which they had a health educator come into the classroom to teach the kids about the bad side of tobacco use. Now, another set of schools got a television intervention in which they watched a television program, presumably about bad things about school. Now, one set of schools got both. They got the combo, as it were. And then finally, there was a set of schools that randomized to not receive anything. That's the control group. So naturally here, what we want to learn about is, do these 2 types of delivery of intervention, the classroom curriculum, the TV, do they have a good effect on knowledge of tobacco use? Okay. Now, if you look at the means, and this tobacco and health knowledge scale was a variable that basically was the number of questions they got correct out of 7. Okay, that's all it is. So it's that you can see a pretest. These are the means across these 4 treatment arms. They're almost identical too. Okay, so 2 out of 7, not all that great, right? If you flip a coin, you should get like 3.5 out of 7 or something. Okay, so that's the means for these 4 treatment arms. And the 4 columns I have here, the first column is kids that didn't get the classroom curriculum, didn't get the TV. Okay, so the next column is kids who got TV. The third is the ones who got the classroom curriculum. And then the final one is the combo, the kids that got both. Okay? So they're all around 2 to begin. And you can see a post-test, which incidentally was about 3 months after pre-test. The control group had a difference of about 1/5 of a point. So they improved to some extent, maybe. Group that got TV, they improved about 1/2 a point. This on average. The group that got only the classroom curriculum got an improvement of about 1 point. Okay? And then interesting, the combo, you might have thought that they would get the best. They're about, similar to, so it just seems like if they got classroom curriculum, they didn't necessarily also need the TV. We'll see. Okay. All right. So here's the multi-level model I'm going to do to begin. And what I want to do is to contrast it and show you how adding in a variable at quote level 1 and level 2, how that works in this multi-level model. Now, what I've written here is what's called the within and between cluster representation of the multi-level model. Here, the idea is at level 1, that's at the student level. Okay, so the dependent variable here is their post-knowledge score from student J within cluster I. And what I'm going to do is to add in their pretest score. Okay, so at first I'm going to begin, I'm not going to have pretest score added in, then I'm going to bring it in. Okay, so that's why I have this bracket around here. Okay, and likewise, between clusters, that's at the cluster level, I can model the intercept in terms of variables. And here I'm going to add in whether or not they got the classroom curriculum or not. And then I have the random cluster effect as well. Now, interestingly, when you write as a multi-level model, you come to realize Well, I could also have the pre-test effect on post-test. That could also be a random effect. What would that mean? It would say this, that the relationship of pre-test to post-test varies across classrooms. Okay? That's possible, right? You could imagine that the pre-test post-test relationship might be stronger in some classrooms and weaker in others. Okay? Reason I point this out is when you don't write it as a multi-level model the way I've written on this slide, you may not realize that's possible. Okay? But writing it out this way gives you that idea that, hey, we could even look at something that as interesting as that. Okay, but let me show you, first of all, a couple of two-level models and what happens when you add in a level 1 predictor or when you add in a level 2 predictor. Okay? So here I'm first showing what's called a null model. Students in classrooms without any covariance. That's why I say it's null. I have a cluster variance. I have a residual variance. I can get the ICC. It's about 10%. So 10% of the variation in knowledge is attributable to the classroom the student is in. Okay? That's what this would say. Here I have it students in schools. Let's look at this null model. Same idea. You can see here the ICC is a little bit less, about 7%. 7% of student knowledge is attributable to the school. So it's a bit more attributable to the classroom, which is tighter than the more diffuse school. Kind of makes sense. Now let's see what happens when I add in a pretest score. This is at the student level. Notice when I add in the pretest score, first of all, it's highly significant. What I have listed here are the estimate and then in parentheses, the standard error. So to get a test, I would take this ratio, compare that to standard normal, do the usual wall test. You can see that that's a Z value of about 10. It's highly significant. So what all that says, if they scored higher pretest, they score higher post-test. No surprise there. But look what happens to the cluster variance and the residual variance. Both of those get smaller. Why? Because I'm explaining some of the variation by knowing what they did on pretest. Okay? I calculate the ICC, it's a little bit less, 9%. I do the same thing, students in schools. Highly significant effect. And again, you see that both the variances are less. That's what's meant by, they're in a sense conditional variances. What's not explained by the covariance in the model. So there's less to explain because pretest has explained some of that, okay? Variation. So the point here I'm trying to make is you add in a subject level variables, it can diminish both variances. Now let's see what happens when I add in a cluster level variable. Okay, so this is whether they have classroom curriculum or not. Okay? So first of all, realize in both of these models, that has a positive effect by about 0.5 point. Okay? So if they did get the classroom curriculum, their post-test scores are higher by about 0.5 point relative to if they didn't. That's a strong effect. Okay? What happens to the cluster variance? It's smaller. What happens to the residual variance? It's exactly the same. Now, when you first see this, it's like, why is that? Well, let's go back to the multi-level model. I'm talking about adding this in. It can diminish the clustering, but because it's at the cluster level, it has no effect on the residual, which is at the subject level. Okay, so again, writing it with this multi-level modeling in mind gives us an idea about what we're seeing here. Adding in a cluster level covariate, as I'm doing here, can diminish the cluster variance, but has no effect on the residual variance, okay? And you can see now the cluster variance, ICC, is about 6%. So what this would say is, and why is that? Because knowing what they received, classroom curriculum or not, has explained some of the knowledge scores, okay? All right, so this shows, again, a couple of points I want to make with this slide. First of all, the clustering effect is typically stronger in clusters that are tighter relative to those that are more diffuse. The clustering effect can change depending on covariance added to the model. And it changes differentially depending on whether the covariate that you're adding is at the subject level or at the cluster level. Okay, now I want to show you here the connection of multi-level model to standard linear regression. So here on this slide, I'm going to write this as a multi-level model. I'm not going to consider pretest. But what I'm going to include here as covariates going to be my classroom curriculum. So this is just a dummy code. 0 if they didn't get classroom curriculum, 1 if they did. Same with TV. 0 if they didn't get TV, 1 if they did. And then the interaction term. And then also the random cluster effect. Okay. Now, what's interesting about writing this, if the cluster effect is completely explained by the condition, then all of these random cluster effects are essentially going to be equal to 0. And then this multi-level model would be essentially the same as an ordinary multiple regression at the subject level, right? Essentially, if this is 0, we're back to multiple regression at the subject level. What's also interesting, though, is if the cluster size here is the same for all clusters, and there's no level 1 covariates as there are here, then this model would be the same as an ordinary regression of the cluster means, what's called a cluster level analysis. In other words, years ago, when people had multi-level data like this and didn't know how to do multi-level data analysis, generally what was recommended is to do an individual level analysis, ignoring the clustering, and then do an analysis of the cluster means and pray that you got the same conclusions, right? And what this slide is trying to show is that both of those are just special cases of the multi-level model. In other words, there's no need to use those which have certain restrictions on them. The multi-level generalizes all of that. And there was some question I think I didn't address. Somebody asked about how does this compare to ANOVA? Well, in traditional ANOVA, typically you're assuming that the cluster sizes are the same. You're assuming balancedness, right? And so, that's where this is and also there you typically don't have subject level covariates in the ANOVA modeling. So this generalizes that. And this slide shows that. So here on the left-hand side, I have here a class level analysis ignoring the clustering of the data. Okay? And here I did an analysis on the student level. I took the student means, first is class level. That's taking the student classroom means. I apologize. Let me back up 20 seconds, erase that tape. So this is with taking the classroom means. So there, the number of observations is 135. 135 means I use that as the outcome. I use these regressors. Notice the only thing that comes out significant is the classroom curriculum. So if they got that in instruction, that helps. Now here in this next, I did a student level analysis, ignoring the clustering of the data. So just ordinary multiple regression, 1,600 observations. I get a significant classroom curriculum, but I also get a significant interaction. Okay. So this would be a situation where these two very traditional approaches, what do you conclude? The one says there is no interaction, the other one says there is. Well, the multi-level model comes to the rescue to give you the proper inference. So here what we learned doing the multi-level analysis is that there is a significant classroom curriculum effect. There's no significant television. There's no significant interaction. Okay? And notice also this from the student level analysis. Notice that residual variance of 1.86. Okay? Here what's done, you can see if you add up these two numbers, the residual variance and the class variance, they equal that 1.86. So basically what the multi-level analysis is saying is, wait a minute, all of this, what's called residual variance is not all residual variance. Some of it is attributable to the classroom that the student was in. And so it's not just random noise. And by doing that partitioning, we've now got more of a proper statistical model that leads to better statistical inference. Okay. Now, finally, I can put pretest in this, and this is what we did in the paper that I've cited here. We had a model like this, had pretest, had these 3 classroom variables, and what we compared in the paper was a class level analysis a student level analysis, ignoring the clustering, student in classroom analysis, student in schools analysis, and then finally a 3-level analysis, students in classrooms in schools. Now, back then when we published this paper, there was not software so available to do these kinds of multi-level analysis, especially for 3-level models. These days, there is. So if one had to choose among these, just based on the design of the study, I think the 3-level analysis is advocated. Why? This is a cluster randomized trial in which the cluster that was randomized was the school. So therefore, we need to account for the school. Okay, so that's what's done here. But the intervention was delivered within the classroom. Okay, so that's what's done here, having the class variance in. Okay, so really the 3-level analysis is, to my mind, the proper analysis. But let's see how things differ as we go across these different models. Okay. So first of all, the class level analysis. This is at the classroom level. Okay. Here we have pretest, but realize this. This is not the relationship of pretest and posttest at the student level, because this analysis is of 135 means of the classrooms. So this is a relationship of the mean pretest from the classroom, the mean pretest, posttest of the classroom. It's not at the student level. Classroom curriculum comes out, nothing else comes out. Student level, doing ordinary multiple regression, ignoring the clustering of the data. Everything comes out. Right, so that's why this data set's a really useful one. If you did these two traditional things, you wouldn't know what to figure out. Television here is significant, here it's not. Interaction here is negative and significant, here it's not. Okay. In the multi-level models, you go across these three. The conclusions are rather consistent. Pretest is always significant. Classroom curriculum is always significant. And at best, there's only a marginally significant interaction of classroom curriculum and the television. Okay. It's only at between 0.05 and 0.1. Now, some of you might have heard that terminology. It's approaching significance. Have people heard that? It's approaching significance, right? Well, I remember one time a very astute person said, wait a minute. Maybe it's not approaching statistic. Maybe it's running away from significance, right? We always think that it's going in this way. It's almost there. It's almost there. Well, maybe it's going the other way, right? In any case, it never gets to 0.05. Okay. So that's the important thing, and really why the multi-level analysis is so useful for multi-level data. If you ignore the clustering, you're likely to make a type 1 error. You're likely to determine that there are significant effects when there really aren't. And why is that? Because the student level analysis, which ignores the clustering, its standard errors are based on assuming that the data from these students are independent of each other. Okay, so if you look at the standard errors here for the classroom curriculum, for television, for the interaction, you can see that they're appreciably smaller than in the multi-level model. Okay, so that's why it's important to take the clustering into account to get the right p-values, the right conclusions. Okay, so the results here, the conclusions is for sure the about the interaction. There's significant differences between these approaches. Okay, now the student level analysis, their estimates are kind of close to multi-level, but the standard errors are not quite so similar, and this is to be expected. This underestimation of standard errors by the ordinary regression analysis, because again, the student level analysis is assuming that the observations are independent, and they're clearly not. Now, from this analysis, we've seen that students are more similar to each other within classrooms and schools. These ICCs kind of bear that out. And actually, the 3-level model is pretty close to the students within classrooms model. Okay? But again, I think from the design point of view, the 3-level model is most appropriate because the randomization was at the school level. Okay? And here show how you can calculate ICCs from the 3-level analysis. You can get, okay, well, how similar are students within the same school? We take the school variance, divide by the sum of the 3, we find out, oh, about 2% of the variability is attributable to the school. students within the same classrooms. Okay, so here we add together the classroom variance and the school variance. We say that, oh, students in the same classroom, about 5% of the variable is attributable to the classrooms. Now you can also get this is not as commonly reported, but you can get an idea of, well, how similar are classrooms within the same school? Here you would take the school variance, divide by the sum of the class and school variance, and say about 30%. Okay, so this is how similar are classrooms within school. They're rather similar. You can also get R-squared kinds of measures from these multi-level models, and this is coming from a classic by Joe Hoax, published in, I think this is actually first edition. I think there's a second and possibly a third edition. What you do is you run first a null model that has no covariance. Okay? And then you run your model with your, say, P covariates, and then you can get a level 1 at the student level. How much of the variation are we explaining with our P covariates? Well, here we're explaining about 7% in what I've just shown. At the classroom variance, to the same kind of idea, I'm explaining about 50% with those covariates. Okay, so I'm explaining a lot of the reasons classrooms are different from each other in terms of the knowledge. I'm explaining a bit less about students, of course, because students vary considerably more. And likewise, you can do the same thing with the 3-level model to get how much of the variability at the student level, at the classroom level, at the school level is my 3-level multi-level model explaining. So again, I'm explaining about 7% at the student level. I'm explaining about 25% at the classroom level and about 75% or so at the school level. So I'm doing a pretty good job at the cluster levels, but really, as you can glean, there's many more reasons why students score differentially on this knowledge. I mean, the only variable I have in here is their pretest, right? So there could be many other student level characteristics that could explain some of the variability. Any questions before I go on? I guess maybe I should ask.
Yes, Kevin, would you like to ask the question yourself?
Yes, sure. I just had a question following up on data structure. You mentioned about there is no need to have the same, sample within clusters. How about longitudinal data? In order to keep time period consistency, is it important to have the sample size within groups to be the same and just report as missing values, those that we don't have?
Yes. Really, that's how I got into this mess, was I was dealing with longitudinal data that had missing data, because that's all longitudinal data on humans. There's missing data, incomplete data across time. So yes, these models allow for incomplete data across time. So you have a study with 5 time points. Some have 5, some have 4, some have 3, 2, 1. That's all permitted. Yeah. Additionally, with this models, time doesn't even have to be discrete like that. It could be continuous. Where I've gotten into that, we've done studies like this on adolescents where we measure them, say, at 7th grade, 8th grade, 9th grade, 10th grade. And instead of using the year as the timing variable, we use their actual age as the timing variable, because kids that are in 7th grade, they're not all the same age, right? There's some variability in terms of their age. Some might be 13, some might be 14 or whatever. So time can be discrete. It also can be continuous, and there's no assumption that the number of time points per subject, that's equal.
Okay, thank you.
Mm-hmm. Okay.
We have another question from Hedeker. Are you here? Would you like to ask the questions? The question here is, how do you conclude that the MLM model fits the data better than the OLS?
Yeah, okay, good question. And I kind of didn't get into that so much. Well, all of these models can be estimated by maximum likelihood. And that sort of leads to the next thing I want to mention. We can do likelihood ratio tests to compare models and decide which is a better model or not. Okay, so realize the likelihood ratio test is a very useful model for comparing, say, model 1, which is nested within model 2. And for example, if I look at this output, this model here student level model here. This is nested within any of these multi-level models because it doesn't have these additional variance parameters, okay? So I can do comparisons as we're just going to do to address that question. So let me show you that. So all of these models were analyzed using maximum likelihood estimation, and therefore I get likelihood values. And what's listed as a deviance is -2 times the log likelihood that I get when I run and estimate that particular model. So here shows student level. Okay, so that's ignoring the clustering of the data. Here show my two-level models, students in classes, students in schools, and then finally my 3-level analysis. What I have as CM here is comparison model. So, for example, if I want to compare students in classrooms versus the student level model, I can take the difference in deviance, and that's a chi-square statistic. On here, 1 degree of freedom. Why 1? Okay, if you go back to this slide here, there's one additional parameter here, students, the variance attributable to classroom relative to the student level analysis. There's one additional parameter. So going from here to here, we're testing whether this parameter equals 0. In the student level analysis, you're assuming it is because you don't have it. In the students in classroom model, you're adding that in. And so now by comparison, we're determining which of these two models fits better. And what we find is that's highly significant. That rejects model 1 in favor of the multi-level model. Likewise, I can compare the students in schools 2-level model to the model that ignores the clustering of the data, the student level model. I get a rather similar chi-square value, highly significant. I can compare the 3-level model to the student level model. Now here's a chi-square on 2 degrees of freedom because in the 3-level, there's a variance for classrooms, there's a variance for schools. There's 2 parameters, highly significant. So the multi-level model clearly beats the ordinary regression model, any of these 3 versions. Now I can also here, interestingly, compare the 3-level to say the student in classroom model. Okay, because the student in classroom model does not include the school variance. The 3-level model has classroom variance and also has the school variance. So if I do that comparison, I get a p-value here of 0.1 or so. And then you'll notice I have this halved p-value. What's that all about? Well, realize this, when I do this comparison, the null I'm testing is that a variance is equal to 0. That's the null hypothesis for these. Well, if you do the ordinary test, you're doing what's called a 2-sided test. The alternative hypothesis is that the variance does not equal 0, but a variance can't be negative. So what you really want is a 1-sided test here. That's what these halved p-values are, okay? So those are appropriate here where you're doing null hypothesis testing about variances. And they're essentially one-tailed p-values. And so if I compare the 3-level model to the students in classes, you can see it's pretty much right at the 0.5 level, okay? So this is how we can do model comparisons, doing likelihood ratio tests between these. And here we clearly see that multi-level modeling vastly improves over the ordinary multiple regression modeling. Okay, summarize this augments multiple regression models by including random cluster, and we're going to get to subject effects now in longitudinal. Okay. And they've also been developed for non-normal outcomes. So here I've just done for normal outcomes, but realize the software is out there for what are called generalized linear mixed models with these different outcome types. And also what I've shown you is hierarchical structure, but you sometimes might have what's called cross-classified multi-membership or different kinds of clustering. For example, you might have students clustered within grammar schools and high schools, but not every kid from the same grammar school went to the same high school. Okay? So those 2 kinds of clustering, the primary school, the high school, they could be crossed, not hierarchical. If you're interested in that, I worked with a couple of researchers from San Diego, actually, on a paper that we published in Psych Methods. There's software out there, many different places to estimate these models. And for continuous normal outcomes, they're generally doing pretty much the same thing. That's not always the case for the non-normal outcomes. There, what I generally recommend is what's called full maximum likelihood estimation using Gaussian quadrature estimation. That's embedded within Stata. That's embedded within some of the SAS procedures. That's not the default in SPSS, nor in some of these others. It is in the program Supermix. I'll say a little bit about that a little bit later. Okay, well, we have about half an hour left. I don't know that I'll get through everything in longitudinal, because realize once you get into longitudinal, it's a big, long building, right? This is a topic I've been working on for a long, long time. But it could be worse. We could be in mathematical lands and either in plane geometry or solid geometry, right? So be thankful we're in multi-level. Okay, so why do people do longitudinal? Well, it economizes on subjects. Subjects are seen to serve as their own control. We can get more efficient estimators than from cross-sectional studies. And we can sometimes separate aging effects that changes over time within subjects from cohort effects. Differences between subjects in terms of different ages at baseline, right? If you have a cross-sectional studies and you see an age effect, you don't really know, is it as a person age, are you seeing that effect? Or is it just that 20-year-olds and 30-year-olds are different? And we can also get estimates of individual change. Now, some of the challenges is that observations are not, by definition, independent. They're correlated within subjects, so we need to account for that correlation. And we also need to consider the variance covariance of the repeated measures. Okay, so often in longitudinal, we're going to look at the variance of the dependent variable across time, and we're going to need to model that. Okay, the models can be a bit more computationally intensive, and that's especially true for non-normal outcomes. For continuous outcomes, not a big deal at all. And then we have to think about, to some extent, this point that's been raised about unbalanced design, missing data, attrition. Now, I did say that these methods allow for missing data and attrition, which they do, but they do make assumptions about that. And there are various ways to see the sensitivity with regard to those assumptions. Now, I don't think I'll be able to get it in great detail in the next half hour or so, but if you do have interest, in my book, I have a whole chapter on this issue of missing data. And we'll talk a little bit about time varying covariates. And then in some studies, there are what are called carryover effects. So longitudinal provides really a wealth of opportunities. Let's not call them challenges. Let's call them opportunities. So opportunities for learning. Okay. Really, one can think about a couple of different things when you're modeling the mean response. So again, we're going to use a regression representation. And now when you have regression, realize, of course, the X variables, they could be categorical, they could be continuous, could be group, could be age, something like that. Now, an important predictor in longitudinal is time itself. And what I'm going to show, two ways of treating time. One is to use what's called trend analysis, using things like linear, quadratic, polynomial trends. I'm also going to show where I have indicators for time point, where I'm going to treat it more in a categorical way. Okay? So these models allow for both. Now, which one do you use for a given data set? Well, what's your scientific question? Are you interested in trend across time? And do groups differ in terms of the trends? Are you interested at just change at each follow-up, say, relative to baseline? Okay? So you want to decide on that in setting up your analysis. Okay? And again, you might have predictors that are time varying or time invariant. Now, we also need to consider the variance covariance structure of the longitudinal data in longitudinal data analysis. Okay, so it's the variance of the outcome, again, conditional on the covariance in our model. What I'm going to show you briefly is two approaches. One is with the multi-level or mixed model, okay, which allows for random effects into the model, and therefore has the variance covariance structure that I've given here. And what we're going to look at is random effects, random subject intercepts, and time trends. Now, an alternative approach doesn't include random effects at all, but instead just posits some kind of structure for the residual variance covariance. So I'll compare these two. Now, another way that you might have heard about, and somebody asked kind of a question about this, where the variance covariance is treated really as nuisance and you're not interested in it. Okay? And just to get robust standard errors. Okay? And really the generalized estimating equations falls within this class. Okay, so here in GEE models, you're really just interested in this. And what you want is to get inference about the betas that's reasonable. But you're not interested in the variance covariance structure at all. You're not interested in random effects. So you don't care about getting individual estimates of subjects' trends. So that's, again, a consideration in going into analysis. What do you have scientific interest about that helps you decide which of these approaches to use? Okay, so here I'm going to use a longitudinal clinical trial from schizophrenia, in which the outcome, it's kind of a quasi-continuous measure of severity of illness going from 1 to 7. The groups, there's two groups here. There's a placebo group, and there's a group that was received one of 3 different antipsychotic medications. Okay, so here I'm putting them together. And so I'll just have a simple grouping variable, drug or placebo. Okay. Reason I did that was I looked at all 3 and they had rather similar effects. Just so to make my life a little easier, I put these together. Okay. Now the sample was measured at baseline at week 0, 1 week later, 3 weeks, and 6 weeks later. Now, interestingly, if you look at how many people made it to week 6, that's what I'm calling completers here. About 2/3 in placebo group, 80% in the drug group. Now, we did a whole paper about this in Psych Methods in '97, myself and Robert Gibbons, where we focused in on this aspect, this attrition aspect. So if you're interested in that, it's a paper from 1997 in Psych Methods, myself and Robert Gibbons as authors. Okay. Here shows the means across time for these two groups. So baseline, 1 week, 3 week, 6 week. Okay. You can see they're going down. So they're improving. And it looks like they're improving faster rate for the drug group relative to the placebo group. Okay, so that's naturally what we're interested in. Is the improvement between these two groups, is it different across time? Now here's the mixed model or multi-level model I'm going to fit. I'm going to do a trend analysis here. So I'm going to have a linear effective week coded 0, 1, 3, 6. I'm going to have the square to allow for quadrature, for polynomial trend, curvature. If you look at the means, they don't look exactly linear. Then I'll introduce drug, the two groups, and then drug by time interaction, both drug by linear, drug by quadratic. So naturally, the parameters of most interest, beta 4, beta 5. Do they have differential trends across time? And then here, I'm going to have random intercept, random linear effect, random quadratic, 3 random effects at the subject level. So what this is going to allow me to do is to get trend lines for every single subject. So I can look in terms of the betas, what's going on at the population level and make inference about that. Drug or placebo, does that matter? But I can also look at individual subjects. Who is improving at a fast rate? Who is not improving so fast? Okay. So this is what I can learn with the multi-level or mixed model. I can get estimates both at the population, the betas, but also at the individual level. Okay. Now, what I want to contrast that to is what's called a covariance pattern model. And I want to do 2 different things here to illustrate for you these different possibilities. For one, in the covariance pattern model, there's no random effects. Instead, what we have is a residual variance covariance matrix. 10 parameters. Why? 4 time points. 4 variances and 6 covariances between the 4 time points. Okay. And so what you can think of is this is like a regression model, but instead in a normal regression model, you just have a scalar variance, right? Just one variance. Here we've got a matrix because this is longitudinal data. And in terms of the mean structure, what I'm going to do instead of doing a trend analysis is I'm going to have indicators for each of the 4 weeks and then drug by those indicator interactions. Okay, so what that's going to tell me about is, are the drug group relative to placebo, are they different at week 0? Are they different at week 1? Are they different at week 3? Are they different at week 6? Okay, so the mixed model I have here is going to say, do they have different trends? This is going to be more focused on finite time points. Are the groups different at these very specific time points? So two different ways of thinking about things and modeling. Here are the results. So here, the multi-level model, again, I'm listing estimates, standard errors. So realize this, for these first 3. So let's go back, sorry, to the equation. That's about these. These are the time trend parameters when drug equals 0. That's for the placebo group. So placebo group starts off severity of illness about 5.3. They improve linearly by about 1/5 of a point per week. That's a significant effect. The quadratic, it's not significant. The estimate divided by the standard error, that's nowhere close to the critical value of 1.96. So what you can learn about the placebo group, they're improving by about 1/5 of a point per week. So 5 weeks out, they improve by 1 point. What about the drug interactions? First of all, the drug effect. This is the drug difference relative to placebo when week equals 0. This is at baseline. There's no difference. Well, it's a randomized trial. At baseline, they should be different, or should be the same, sorry. Drug by linear time, negative and highly significant. So their linear descent, linear trend, they're improving at a much faster rate than the placebo group. Quadratic, it's positive and significant, meaning that their rate of improvement isn't quite linear, it's curvilinear, right? It's a decelerating negative trend. Go back to the plot, you can kind of see that. It's a decelerating negative trend that you're seeing for the drug group. It beats the placebo group. All right, so that's the trend analysis with the mixed model. Then doing this specific time point comparison kind of approach. Again, here the weak main effects would be when the drug variables coded as 0, that's the placebo group. This shows the mean for the placebo group at these 4 time points. They start off around 5.4, they go down to 5, then 4.8, 4.4. Okay. So that you can see some improvement. These are the actual mean estimates for these 4 very specific time points. Now we have drug versus placebo comparisons at each time point. At week 0, there's no difference. At week 1, there is a significant difference, and that's about 0.5 a point. At week 3, significant difference, it's about 1 point. At week 6, it's almost 1.5 points. Okay. So again, these are showing 2 different ways of modeling the mean structure and what you're learning. With the trend analysis, you're learning about the differential polynomial trends across time. With the mean model specification, you're learning about comparisons at particular time points between the groups. Okay. Now, I won't go over this in great detail, but this is the estimates of the variance-covariance structure between these 2 modeling approaches. The mixed model, the multi-level model, it directly separates the between subject variance from the within. The variance of the random effects are the between subject variance. It's telling us, is there heterogeneity across subjects in terms of the intercept, the linear trend, the quadratic trend? And are those things associated with each other? That's what the covariance can tell us about. Now, in the covariance pattern model, it's there's no separation of the between and the within. We just get a 4x4 variance covariance matrix, which is the residual variance covariance. Okay? So again, two different ways of treating the means that I've done here, two different ways of treating the variance covariance structure that I've done here. Okay? Now, here's an advantage of doing the multi-level or mixed model, as I've mentioned. In the multi-level mixed model, we can get trend estimates for every single subject. So, for example, on the left-hand side of this plot, I show the plot for the placebo subjects. Okay? Their estimated trends across time. So what you can see is this. There's some placebo subjects that do extraordinarily well. Some that don't do well, right? On the right-hand side, I have a similar sort of plot for the 300 or so drug patients. Again, there's some that do really remarkably well, but interestingly here, there's some that don't do so well. Now, the reason I point this out is when you look at these tests where drug beats placebo, you might be thinking, oh, drug works best. It does work best on average. Doesn't mean that it works for everybody. The mixed multi-level models with these individual estimates shows the heterogeneity of the response across time at the subject level. And you can see there's a great deal of heterogeneity really for both groups. So again, placebo, there's some people that do quite well with placebo for whatever reason. And again, with drug, there's some people that don't do so well. And that might be of interest to explore that further. So this is just exploratory, but you might want to take that further to say, is there something about the placebo subjects that did remarkably well that maybe I want to incorporate in my modeling? Or is there something about these drug patients that didn't do so well? Now realize this, if I do a GEE analysis, or if I do a covariance pattern analysis, I don't get this information. So this is really what you can get with the mixed or multi-level model, the random effect estimates, the trend estimates, these that can be of interest in some cases. Now you might say, one really nice thing here in the way I treated this modeling is that I get estimates of the drug relative to placebo, the difference in that at every single time point. That is kind of a nice thing to get. It's very interpretable. Can I get that from the trend analysis that I did? Yes, I can. Here shows the modeling of the trend model that I considered. Well, realize here I have three parameters about the group difference: drug, drug by time, drug by quadratic. So I can figure out, well, what's the drug difference for any value of week? So for example, I want the drug difference at week 6. That's the last time point. The answer to that would be beta 3 plus 6 times beta 4 plus 6 squared, 36 times beta 5. So it's just a simple linear combination of the parameters from this trend analysis. And in Stata, I can use lincom to get that. In SAS, I can use estimate to get that. And if I do that, what I get is an estimated difference between the two groups of about 1.5 points at the last time point. Here's the estimate, here's standard error. And if you go back, you'll see that's almost exactly the same as what I got with CPM. Okay, so realize from the trend analysis, I can also figure out what's the difference between the groups for any value of time. So I'm not restricted to just comparisons of the trends. I can additionally augment that and get, well, what are group differences at important time points? Now, finally, what I like to also mention is something about effect sizes. So it's often of interest in longitudinal to say, well, what's the effect size, let's say at the last time point? In drug trials, for example, they often treat the last time point as the end point. So here, I'm going to calculate Cohen's d, which is basically the difference in means divided by the common standard deviation. Okay, that's Cohen's d. And here, what that will be is the estimated group difference at week 6 divided by the estimated standard deviation at week 6. Okay. Well, from the CPM, I have that estimate, minus 1.44. Okay, so where did I get that? That's this. And where do I get the standard deviation for the last time point? That's this. This is a variance, so I take the square root of that. Okay. And I get an effect size of minus 1. Now, if you recall with Cohen's D, anything like over 0.8 in absolute magnitude, that's a large effect, right? Usually it says 0.2 is small, 0.5 is medium, 0.8 is large. This is a big difference. So this is, not only is it statistically significant, it's clinically very meaningful too. Now, what about for the trend analysis that I did with the mixed model? Well, again, I showed you on the previous slide how we can get what's the estimated difference at week 6. It's just a linear combination of parameters. So in Stata using LinCom, in SAS using estimate, I can get this value. Now to get the standard deviation at the last time point, it's a little more work. But if you do that work, and here I did it with Meta in Stata or IML and SAS implementing this equation here, I get this for the variance at the last time point. I take the square root. Notice I get almost identical value for the effect size at the last time point. So basically, in terms of a standard deviation, the drug group is 1 point below placebo at the end of the study. That's a big effect, a big benefit. Okay, so just to summarize, what I've shown here is 2 different ways really of modeling the mean structure in this brief introduction to longitudinal. I should tell you this. I teach a week-long summer course on longitudinal in which we go through a lot more than this. I've tried to summarize this in half an hour. Obviously, I can't touch upon everything in half an hour, but maybe this gives you a flavor of some of what's involved. So you can do trend kind of analysis. We can do comparison to baseline. We can do time point indicators. What I've done here with this example is do trend analysis and time point indicators. Okay. We also need to consider the variance covariance structure. Okay. What I've highlighted here is to do that with the mixed or random effects modeling. And what that allows is we can get estimates of subject trends across time. Okay. And it also separates the within and the between subject variance. And it tells us about the heterogeneity of the trends across subjects. Okay. Now, alternatively, when I did the covariance pattern model, we just directly look at the residual matrix. So we don't get random effects. But instead, all I did was say, oh, I have 4 time points. Let's just get a 4x4 matrix there. Okay. Okay. That's also a nice approach. And again, the third kind of general approach is where you're considering the variance covariance structure as nuisance. So something like the GEE, okay? And or getting robust standard errors. So for one thing, you don't get random effects, so you don't learn about subject trends. You don't learn about heterogeneity. And actually, in terms of missing data, you're making a stronger assumption with the GEE approach. You're assuming what's called missing completely at random rather than just missing at random. Okay, so there's some benefit for doing the full likelihood, either the mixed model or the covariance pattern model vis-a-vis the missing data. And here, this point is kind of made here. These methods do allow for incomplete data across time. We are assuming MAR using full likelihood estimation, but realize again, that's preferable to what's done with GE, which assumes missing completely at random. Now, if you suspect what's called missing not at random, and realize it can only be suspected, because what it means is that the missingness depends on what you have not obtained, the missing data. Right? So you can only think, maybe this is happening. If you're interested in that, I would again urge you to look at that 97 psych methods paper that I worked on with Robert Gibbons. It describes what are called pattern mixture models, which shows kind of a practical way of doing sensitivity analysis to see how much does this play a role. And I use the same example, the schizophrenic study, in that particular paper. And then finally, I just want to say that today in this short hour and a half, you might say short, God, this was crucially long, right? I've focused on normal outcomes. Well, of course, we can also do much of this work for non-normal outcomes. And really a lot of my research that I've done over the years has focused on non-normal outcomes, binary, ordinal, nominal counts. And much of this methodology does extend to those methods as well. Okay. So let me just finish with just mention a little bit about software, and I'm happy to answer any questions that we might have. Here I just provided some references for SAS, SPSS, and Stata that one might pursue for how to do these kinds of mixed models, these multi-level models in these different software packages. I mentioned a little bit about the SuperMix program. It's distributed by Scientific Software. It's a package that I've helped with. There's a free trial, 2-week trial you can look at. Again, there's other programs, HLMs out there, MLWin. In R, there's LME4. So there's many possibilities these days for estimating these kinds of models. So I see I'm pretty close to 30, or I guess it would be 12:30 your time, but I'm happy to address any question. And I apologize about going a little bit fast over this longitudinal part of the workshop today. Okay.
Thank you so much. It got me interested in taking your summer classes, longitudinal data.
Okay. Yeah, that'll go on a little bit longer and cover things in more detail. Okay.
Minu, go ahead.
Thank you, Don. Thank you very much for spending time with us in this group. Before we get into any other sort of questions, I just want to get this information out of you so that everyone knows about it. So I was able to take the advantage of your course with Statistical Horizons for MLM. So that's how I took your course.
Okay.
So I don't know if you're still doing that for MLM and for longitudinal. Could you just talk to the group about where they can take the classes if possible?
Sure. The easiest way to find out is if you go to my sites here, my website. It has links, and I'm teaching actually 3 workshops this summer. Let me say the first is let's see, the week the week of June 12th through 16th. I'm doing a week-long summer course via University of Michigan. That's going to be a hybrid format, and that's ICPSR is where it's at. University of Michigan. Again, you can get to that link via my website there. That's a 5-day course that goes through what I've presented here, but much more. Then I'm also doing 2 workshops for Statistical Horizon that you mentioned, Manu. In the one that you mentioned, I'm doing for 3 days from June 26th through the 29th. I guess that would actually be 4 days. I don't know how to count. I just know how to do matrix algebra. I forgot how to count. That's going to be strictly online version. So that's going to be the 26th through the 29th of June. And then in late August, I'm going to do one on what's called intensive longitudinal data from the 22nd of August through the 25th. So again, that's 4 days. That's on these data where you get not 4 or 5 observations per subject, but it's like mHealth data where you get 30, 40 observations collected via smartphone, things like that.
Thank you, Don.
Sure. Yeah.
Thank you so much. Thank you everyone for joining us. And I just want to mention, like, today's talk will be recorded and shared with all you later. It's 12:30, and we have some burning questions here from the audience, and we will see you next time.
Okay. Thanks so much. Appreciate it.
Thank you. Have a good weekend.
Thank you, Don.
Okay.
Have a good weekend.
All too. Thanks. Thanks so much. Yeah.